This module will cover Ethernet switching. The topics covered within this module are we will be explaining the Ethernet frame, the physical address, which is an Ethernet MAC address in this case, how a switch is going to build his own MAC address table, and what are the methods used to forward the Ethernet frame and explain the switch speeds. Start by explaining Ethernet frame. As you know, we covered the OSI reference model in the previous module. OSI reference model is divided into 7 sublayer where every sublayer is going to tackle a certain functionality independent from the other functions related to other sublayer, and a sublayer is going to provide services for the upper layer and require functionality and services from the below sublayer. So in the previous modules, we passed through the physical sublayer with its different transmission medium related to either to the type of media, either it's a wireless transmission medium where the data generated by a sender is going to be transported through electromagnetic wave. We saw also that we have a copper wire, either twisted pair or coaxial cable, where the data generated by an end device is going to be transmitted through an electrical signal. And the third transmission media is the light, which is a fiber optic carrying data as light. With these three different media, everyone it has different behavior to carrying data depending on the nature of the transmission medium. For instance, if we take the wireless medium, this type of a transmission medium is subject to interferences, it's subject to lower performance depending on the time and the weather. If it's we're deploying a wireless connectivity outdoor, if we're implementing it indoor, we will be facing obstacles while spreading the signal within indoor. So it might generate errors. Similar to wireless, copper wire also carrying electrical signal also might face multiple problems due to interference, to noises added to the original signal carrying user data. The most robust one and reliable one is the fiber optic, but it has its own drawback, which is the cost of fiber optic. So, who's going to recover from the error due to the transmission on the physical transmission medium? Who is going to recognize the sequence of bit into something understandable, something it has significance, such as the MAC address source, the MAC address destination, which is the physical address source, and the physical address destination, all and much more features. This is the role of the data link layer. The physical layer and the data link layer are covered or standardized by the international organization IEEE, where the data link layer is divided into two sublayers. The upper sublayer is going to be represented by the standard 802.2, or providing services such as LLC, it stands for Logical Link Control, which provide and receive the request from the upper layer to provide services for the upper layer, while the lower sublayer, data link sublayer, which is a MAC sublayer, it stands for medium access control, which will be part of IEEE Ethernet protocol defined by 802.3 and its different variants. So as mentioned before, the data link layer as per IEEE standards, they divide into two sub-layers. We have the upper sub-layer, which is the LLC sub-layer, which provide three different services required by the upper layer, which is the network layer. And it's standardized by IEEE 802.2 standard. The max sublayer, the below layer, the lowest sublayer of the data link layer, will be part of a standard, either it's 802.3, which and its variants cover Ethernet, where the transmission medium is copper wire, twisted pair, or fiber optic. We have the Wi-Fi, what you have at home, or even in a public network or at work, which is 802.11 standard and its variant. And we have the wireless band, which is 802.15. It stands for Bluetooth, and not everybody is using Bluetooth while connecting his AirPod to your smartphone, or maybe to your connecting your printer through a Bluetooth connectivity to your PC or even to your smartphone. So the MAC sublayer is responsible for data encapsulation and accessing the media. Not only, it has also, what do we mean by data encapsulation? Which means that if data is sent from the receiver, from the sender, is going to start from the upper layer, from the application layer, is going to be encapsulated from while going down to the bottom, from one sublayer to another, from one layer to another layer, to reach finally the MAC sublayer before going to be transmitted over the transmission medium as data, as a series of 0 and 1. And how is going to access the media, how is going to control the access to the media, how we can recover from the errors due to the media. So we start with the data encapsulation. It will include the format of an Ethernet frame, how we format the frame from the sequence of bits coming from the physical layer, when it start, when it finish, how many feeds we have inside, how many bits the size of an Ethernet frame should be. This is how we format the Ethernet frame. The second point is the physical address, which is a MAC address, is going to be encapsulated within the header of the Ethernet frame, and it's going to be transmitted from your device, from your network card interface, or network interface card, to the destination NIC card, if they are on the same LAN, or it's going to cross a wide area network when it reaches your destination, if they are both not on the same LAN. Third point is how Ethernet is going to detect the error to be able to recover from errors. This is going to be used, provided by a frame check sequence or FCS put at the end of an Ethernet frame called trailer. And the aim of FCS is to detect error. Also, MaxUp layer it aims to control the media access or access to the media, independent from the type of media, either it's wireless or copper wire or it's a fiber optic. In the legacy Ethernet, the first version of Ethernet, the physical transmission medium was using a topology which is a bus topology, which means you're going to pull a coaxial cable and you drop a coaxial cable along a room, and you start by connecting every network interface card to this coaxial cable. Imagine the coaxial cable what you have at home, which serve you to connect to the dish. It is the same, exactly the same cable. It is the coaxial cable, and you pull it around the house, and whenever you need to connect a device to the network, you take your interface card embedded within your device with a drop cable terminated by a transceiver, and you're going to insert it inside the coaxial cable to get access to the wire inside the coaxial cable. This is the physical connectivity. This coaxial cable is going to be shared by multiple end users. So when it's come to sharing data, you cannot transmit and receive simultaneously, since you will have some issues. So to avoid these type of issues, you will be transmitting and waiting for the other to receive your data. So we call it the half duplex medium, which might create accident. Imagine two hosts start by transmitting simultaneously. Uh, since data it's an electrical signal, or even going to be with a bus topology, it's a coaxial cable, it's a copper wire, so the data is going to be transmitted over it using electrical signal. So two frames somewhere they will get in contact and there will be a collision, such as similar to a car accident. So someone has to detect this collision and to notify other hosts that there is a collision, and to also to manage and to control the access to the medium to avoid such collision. This is done by the protocol CSMA-CD. It stands for Carrier Sense Multiple Access Collision Detection, which is a contention-based access method. Today, Ethernet, with the advancement in the physical topology, where we move from a bus topology through a star topology, where we have a centralized node called a switch, and within the switch, it is done. It's made with an aim to avoid the collision, to avoid having any uh, delays or errors. So we moved from a half duplex medium to a full duplex medium, and we'll see why also when implementing Ethernet switches, since the collision is going to be avoided, completely avoided, so it's not required to use this SMACD, but still it is implemented within your network card interface, always to be backward and compatible with older version. So with that one of the aim behind Ethernet protocol is to create an Ethernet frame which means from the sequence of bits received over the transmission medium on the physical layer, we need to build to reconstruct or to group this different part of sequence of bits to create something significant and something useful to be used. And we said that layer 2 it aims to define a physical address to identify a host, a sender, and a receiver. So while collecting these different bits, we can find the following. We talked before about PDUs, a protocol data unit where when we do encapsulation, start from the application layer, going down, encapsulating from layer to layer until we reach a physical layer. In fact, every layer, the protocol related to every layer is going to build a PDU, a protocol data unit, which is made from a header and a payload or a data field. So the header, it will be made mainly having addresses, and the payload will be carrying data coming from the upper layer or directly from the end user if we are on the application layer. When we while encapsulating and going down from application to the below layer until we reach the data link layer. In fact, data link layer also, it has at the end of the frame or the PDU, it has a trailer. Okay, the trailer and the header both will help to delimit to give a limitation or delimitation of this of an Ethernet frame. So if we look at the frame, we have the first 8 bytes called preamble and start frame delimiter. These 8 bytes will help providing synchronization between the source and destination while using the encoding schema. You remember we talked about when we encode, we use like Manchester, we move from minus 5 volt to plus 5 volt in the middle of a time bit, and this is like multiplexing the internal clock rate with the data generated by the end user or by the application. So the preamble and SFT mainly are used to start a frame, to provide synchronization between source and destination, and also to be used for delimitation of the frame. It's not part of the header. Then we have 14 byte, 6 byte after the first 6 byte after preamble and SFD are the destination MAC address, which is the physical address of the destination, with over 6 byte, which means 48 bit. The source MAC address also 6 byte, which means equal to times 8 equal to 48 bits, and we have 2 bytes as type and length field. These 3 fields, destination MAC address, source MAC address, and type length field, form for the header of a data link layer, which is an Ethernet protocol. Then we will have a data field, which minimum size should be 46 byte, in fact, not 45, should be 46 byte, up to 1500 byte maximum value. And we have the frame check sequence, it's 4 byte, which will provide mean to detect errors in the frame. Why I'm saying 46? Because a minimum size frame of an Ethernet frame should be 64 byte. Therefore, if you add 6 byte plus 6 byte plus 2 plus 4, you will have 14, 18 byte minus 64, which will leave you a 46 byte. So the minimum size of the data field should be 46 byte. Here in the lab, you will be using Wireshark, which is an application to capture traffic running on the network, used mainly by security teams to monitor the traffic over the network, which will help you in the part 1 to examine the header fields in an Ethernet frame, and part 2 to capture and analyze Ethernet frame. In this section, we'll be dealing with Ethernet MAC address. So as per IEEE standards, where Ethernet is an IEEE standard, IEEE, they define the physical address as being 48-bit, which means divided by 8 will have 6 bytes. The 8, how it is represented, in fact, the MAC address is going to be represented over 6 byte. Every byte is followed by a colon, okay, and every byte it will have value spanning from 00000 up to 11111111. Which mean a range between 00 and FF on every byte. So either it will be represented as binary or it will be represented in hexadecimal value. In fact, the MAC address is represented in hexadecimal value when you capture an Ethernet frame while using Wireshark. So the MAC address, which is made of 6 byte or 48 bits, divided into 2 parts. The first 24 bits, most significant bits, are used to identify organization, which called organizationally unique identifier. And the second 24 and the remainder 24 least significant bits are assigned by vendor, such as it can be a serial number provided by the vendor to every network card interface created by this vendor. So when a device is forwarding a message to an Ethernet network, when you have to build an Ethernet frame, this Ethernet frame, it's made of the data provided by the upper layer, which is going to be encapsulated within the data field of an Ethernet frame. Add to it the Ethernet header, which is made from the destination MAC address, the source MAC address, and a 2 byte for the type and or length control field. So when a host is going to transmit an Ethernet frame, he should know the MAC address source, which is own MAC address embedded on his network interface card, and he should learn the destination MAC address to be able to build his Ethernet frame to be transmitted to the destination. The frame, Ethernet frame, as it will be broadcasted or multicasted, or it will be transmitted directly from a source to a destination while crossing a switch. So we can find either unicast or multicast or a broadcast Ethernet frame. So when a network card interface residing on your device receives an Ethernet frame, it will start by examining the destination MAC address. If the destination MAC address is equal to your own MAC address, then he will process this Ethernet frame, otherwise he will drop it. So in Ethernet, I said before, either we can have unicast, broadcast, or multicast addresses used for unicast communication, broadcast communication, and multicast communication. Every host, it should have a unicast MAC address. So every network interface card residing on a certain device, any type of device, it has to have a unicast MAC address. So for a source to, I told you in the previous slide that to be able to transmit your Ethernet frame to your destination, you need to build your Ethernet frame. You have to identify your MAC address, so as a source MAC address that you can get it from your network interface card, and you need to check for the MAC address of destination. So you might know the logical IP address, but you don't know the physical MAC address. So now here you rely on a protocol known as address resolution protocol. Having the MAC address of destination, you're going to broadcast an ARP request asking who has this network address, provide me with your physical address. This is done in IPv4. In IP version 6, there is another protocol similar to address resolution protocol, which is the neighbor discovery protocol. And here the source MAC address should be always a unicast MAC address. A broadcast MAC address where all the 48-bit of an Ethernet address is going to be equal to 1. Which means that the destination MAC address, if it's a broadcast, it should be all F in hexadecimal value. When you transmit an Ethernet frame with a destination MAC address is a broadcast MAC address, so it's going to be broadcasted to all ports while crossing a switch, except from where it comes this frame. Okay, we will see next multicast address, which is a destination MAC address if it's encapsulating an IPv4 multicast packet. So the MAC address destination will be 01005E. Where do we use multicast MAC address? We use usually multicast Ethernet address or MAC address for specific application, such as the spanning tree protocol. It's used for resolving loops in the network while having multiple switches interconnected together. We will explain it later on. So to deploy the spanning tree protocol, we need to have a multicast IP MAC address. So the multicast address, in fact, the unicast address is a unique address configured and identifying a certain device. While the multicast address is a group address where multiple entities may have the same multicast group address, or when you transmit a frame where with the destination address is a multicast address, all members of this multicast address will be receiving this Ethernet frame. This minimizes the number of same Ethernet frame you have to generate when you're targeting a unicast address, while if you need to transmit the same address for multiple destination, you can provide them with a multicast address group and you transmit using this multicast address group. In this lab, you will made of 3 parts. You will be setting up a topology and initializing devices. On the second part, you're going to configure devices and verify connectivity by pinging devices each other. And the third part you will have to display, describe, and analyze an Ethernet MAC address. For the switch to be able to switch Ethernet, it needs to build a switching table, which is a small database, a kind of database where he can learn MAC address source from frames coming through its port, and he associate the port number with the source MAC address. Whenever he receives a frame, to make a decision either to switch it or to drop it or to switch it to which destination port on the switch, he look up the switching table based on the destination MAC address, and he look for the destination MAC address if it's already in his switching table, and he associated to which physical port number, so he can switch the frame to this port number. So the Ethernet switch is going to examine the switching table at the switching MAC address table whenever he receive an Ethernet frame and he need to forward to a destination. So to take the decision to which destination he should switch it, in fact he look up switching table. I already told you it's an association between a switch, a port number, and the MAC address source received over this frame, which means he learned through this Ethernet frame the MAC address of the host connected to this port number. When he make decision, he look up this table and he search for a destination MAC address based on the MAC address destination within the Ethernet frame. If he has the destination MAC address, so he will forward it to the physical port associated to this entry within the switching table. Otherwise, he has to try to flood it all over the port unless from where it came this Ethernet frame. When the switch is turned off and just turned on, the switching table is empty. He needs to learn the switching table. In some vendor, the switching table is called CAM table or contact addressable memory table. So I'm repeating, the switch is going to examine the source MAC address of every frame received on every port. If he knows the MAC address already, it is within his switching table or CAM table, he updates it if needed. Otherwise, he has to add it. If he doesn't have it, he has to add it to his switching table. In order to forward the frame to the destination, he's going to check the destination MAC address, which is a unicast address in the Ethernet frame received. If it's a multicast address, he's going to flood it to the port number of this multicast group. If it's a broadcast address, destination address is going to flood it all over the port, unless, but not from where it comes frame. If the MAC address is not in the table, he can going to forward it, or we call to broadcast it all over the frame, all over the port, but not from the incoming port. Suppose we have the following address. We have A communicating sending a frame to D. A is connected to the physical port number 1. D is connected to physical port number D. The switching, we suppose here that the switching table is already populated, is already learned with the MAC address of A, which is 000A, is connected to port 1, and 00D related to station D connected to physical port number 4. So when the switch receives an Ethernet frame from A, he looked to the source MAC address to update his switching table either by adding it if it's not already within the switching table, or to update if the physical MAC address, the MAC address is coming from a different port number. Let's suppose A moved to port 2, so he has to update the switching table by adding 000A connected to physical port number 2. To take the decision to which destination port it should forward the Ethernet frame, he looked to the destination MAC address. Destination MAC address states that it's 000D. He looked up the switching table. He found the entry of related to this MAC address, which is connected to physical port